Good afternoon, ladies and gentlemen. I am Archana Thomas with my colleague Zainab Akhter. We're here to talk about our study on design of an oil field produced water treatment plant with the UAE perspective in mind. To give you a quick introduction, let me talk to you about what produced water is. It is the water that surfaces when oil is extracted, and it is estimated that for 1 barrel of oil that is produced, around 3 to 10 barrels of produced water is surfaced. Globally, it is noted that 800 million meter cube of produced water was discharged offshore around the globe in 2003. And we're talking about a huge amount of water whose reuse potential was not properly identified. It is projected that the global oil and gas demand is going to be increased by 37% in 2035, which means more amount of oil is going to be extracted. Now, for every barrel of oil that is produced and refined, 6 barrels of water is required in the process. And this water is usually used in cooling towers for feeding high pressure boiler systems, process water in firefighting, and as potable water. So the issue is, when the global demand increases, the oil and gas production increases, which means the need for water increases. So here we have a quick overview of the composition of produced water, where it is rich in sodium, potassium, calcium, magnesium chloride, total dissolved solids, etc. Produced water is known to be toxic in nature and cannot be discarded off without treatment. Now, to combat this issue of produced water discharge and to combat the need for high amount of water required in oil field treatment plants, we propose to use this produced water in cooling tower systems. Cooling tower systems are known to utilize a lot of water for its to be circulated in its system. It is known that around 2 meter cube per hour of water is required to produce 1 ton of crude oil per day. And as you can see in the table on the right, it summarizes the constituents of cooling tower standards. These standards are recognized keeping in mind the scaling potential, corrosion potential, and fouling potential to minimize these to as low possible rates. So our proposal is to use this produced water treatment plant to treat this water and bring it down to cooling tower standards.
So next we have the process flow diagram for our process, where we have our main equipment to be EDI unit and reverse osmosis unit. But before allowing the water to this equipment, we need to do a pre-treatment. So we have sand filter and activated carbon filter. So the water flows to sand filter from a storage tank at 60 meter cube per hour. From there, the water flows to activated carbon filter. As this two process is a slow process, the water flows and gets accumulated in the storage tank. And then from that storage tank, the water flows to EDI unit, where with the flow velocity of 150 meter cube per hour. The water flows from EDI unit 1 to EDI unit 2, and the final product from EDI unit 2 goes to reverse osmosis unit. But in order to increase the production, we recycle 40% of the waste stream from EDI unit 1 and EDI unit 2 so that we have a higher production. And then from reverse osmosis, the reject stream is being sent for further treatment, while the permeate stream is sent for cooling tower. Next is the material balance for all the equipment that we have used. So for slow sand filter, it removes TOG and TOC, which is total oil and grease and total organic content. Activated carbon filter removes chlorine, TOC and TOG. Electrodialysis reversal system removes chlorine, sodium, magnesium and calcium. And reverse osmosis unit we have for further reduction of the element, which is such as chlorine, sodium, magnesium, calcium and TOG. So further, for the energy balance, we calculated for EDI unit first, which requires current for it in order to run the unit. So we calculated current using the following equations, where we found I using the formula where CF represent feed concentration, CD represent the dilute concentration into Faraday's constant into the dilute flow rate. over efficiency into number of membrane pairs. After finding I, we calculated power using P equals IV, and we estimated the number of stacks required to be 3 because of our high flow rate, and power required by each stack was calculated using power over 3, and the summary, the table shows the summary of all calculations. Next is the energy balance for all the pumps. So here, in order to find the power required by the pumps, we calculated using Bernoulli's equation, where shaft work is equal to the following equation, where delta P is the pressure difference, G is the force due to gravity, and delta Z is the change in height, delta V is the change in velocity, flow velocity, and PL is the pressure loss due to fittings, and rho is the density of produced water. So we found shaft work using this equation, where the shaft work is converted into power by multiplying by mass flow rate, where mass flow rate was calculated by using density into the flow rate of the water. And we found pump power using P over efficiency, which is usually 0.7, and here we have the tabulated values of all the power required by the pumps.
Next, coming to equipment design, we explore the dimensions of each equipment in detail. To start with the two storage tanks that we have, we use heuristics relation for height and diameter, where we estimate it to be 1.5 times diameter. From this, the height was estimated to be 7 and 6.9 meter, and adding an allowance height, we found the total height to be 8.4 and 8.28 meter. And the diameter was found from dividing the height by 1.5 meter. And finally, for the bottom static pressure, P equals rho GH, which is the last formula shown here, was used to find the bottom pressure of both the tanks, which was found to be 78 and 77 kilopascal respectively. Next, coming to slow sand filter, the main variable that was calculated was the outlet pressure and the pressure loss. And the total height of the slow sand filter. The total height was found to be 2.5 meter from literature review. Next, the pressure loss and the static pressure was calculated. Static pressure was calculated using rho GH, as you can see the first equation. Next, the pressure loss due to flow in a slow sand filter was calculated using Reynolds number and friction factor shown in second and third equation respectively, taking into account S shape factor, D grain size diameter, Vs superficial flow velocity, alpha being porosity, and finally using these Reynolds number and friction factor, head loss was calculated, which was converted into pressure loss, and finally the outlet pressure for this filter was calculated to be 187 kilopascal. Next, coming to the pump, as mentioned before, Bernoulli's equation is used again here to calculate the pumping pressure, as you can see in this equation. So, substituting the values of pressure and height difference and velocity difference and the pressure loss in the system, the pumping pressure was calculated for all the pumps in the system, and the pressure loss, as mentioned before, was calculated from Reynolds number and Darcy friction factor, and taking into account the equivalent length of all the fittings used in the system, as you can see in the previous above equations. And also the net positive suction head available, also known as NPSHA, was also calculated. These are the values of all the pumps used in the system are summarized in this table with the diameter, pressure, total head and NPSHA. And coming to activated carbon filter, absorption capacity was calculated with designing a certain effluent concentration, as you can see in the first equation. From the absorption capacity, mass and thereby the volume of the bed was calculated. From the volume of the bed and a standard height of carbon bed, which is known to be 2 meter, the area and thereby the diameter of the bed was calculated. And finally, to find the outlet pressure, first pressure loss due to flow in an activated carbon filter was calculated just like this slow sand filter, taking into account porosity, friction factor, superficial velocity, etc. So thereby this head loss was converted to pressure loss, and the outlet pressure was estimated to be 209 kilopascal. Next, coming to the EDR unit. the number of membrane pairs was calculated using the first equation, and the total number of membrane pairs divided by 600, that is the standard pairs in each stack, the stacks were calculated, and also the height of stack was found to be 2.55 meter using this equation, taking into account cell height, allowance height and frame height. Finally, coming to the RO unit, the total area required for the module was calculated using this equation, where QP represents the permeate flow stream, water permeability coefficient, change in pressure, change in osmotic pressure, which goes back to modified Van Hoff coefficient, feed and permeate concentration, and the total area was calculated, and the standard area per module was also found from literature review, from which the number of modules were calculated, which was found to be 200, and the pressure loss was found to be 1 bar. Next, coming to process economics.
Next is the process economics for our process, where we calculated the fixed capital investment. So in order to calculate the fixed capital investment, we calculated equipment cost first, which has which is related with the capacity. Next is the bay module cost, where it considered the pressure and the material of construction factor. And then we calculate the total module cost, which consider contingency and fee structure as well. And in order to convert the cost into present value, we use the last equations. So the total bay module cost was calculated for all the equipment such as pump, storage tank, filter, EDR and RO was to be $721,000, and total module cost was calculated to be $851. So the total fixed capital investment, which is also known as a grassroots cost, was estimated to be $1.18 million of 2019. Next is the cost of manufacturing, which consider labor cost and utility cost. Labor cost was $573,000 per year for 8 laborers, as our process requires minimum supervision. And the utility cost was calculated to be $833,000 per year due to the electricity. And the final cost of manufacturing was calculated using the below equation, which consider fixed capital investment, labor cost, utility cost, raw material cost and waste treatment, which was estimated to be $2.25 million per year. So according to the previous calculation, we found that payback period was 9.25 and rate of return was 13.83 of investment. So next is the environmental aspect of the process, where we found through literature review that we have two processes to monitor the effect in the environment. First is the CHARM, which is chemical hazard assessment and risk management, which focuses on the chemical that we used for the process itself, and the other process is TIE, toxicity identification evaluation, which checks the chemicals on the final emissions.
And all in all, now to conclude, this study proposes a produced water treatment plant aimed at reusing this huge amount of water, whose true potential was never really identified or studied. And this treatment plant that we propose has a treatment capacity of 1,500 meter cube of produced water per day for an operational time of 15 to 16 hours, which reaches a recovery of 76%. The main equipments in this plant are storage tank, sand filter, activated carbon filter, centrifugal and reciprocating pumps, EDR stacks and reverse osmosis modules. All in all, for the in terms of the investment required for this plant, it was estimated to be $1.18 million with an annual operational manufacturing cost of $2.25 million per year. In terms of returns on investment, the payback period was found to be 9.5 years and the rate of return on investment was found to be 13.83%. Thank you.